convinced into automation? Yeah, you are? Maybe you will be after the presentation, if he can convince you, but automation is a huge topic these days. So the past days we've been talking about automation again and again and again, due to, for example, the talent gap. We need automation, but it's not only for replacing the skilled workers who are just not there. It's much more. But well, let's find out more regarding TIG welding and welcome our first speaker of the day. Please welcome the application engineer at Wolfram Industry, Matthias Schaffitz. Good morning, Matthias.
Thank you for the lovely introduction. So the topic today is how to unlock untapped potential in TIG welding, or in short, are you really using gas tungsten arc welding to its full potential? And I dare to say, probably not yet. Some yes, some probably no. First about me, I'm Matthias Schaffitz. I go with the name Matthias, preferable. So I'm an application technician and essentially welder by training. I'm also a qualified welder, operator, non-destructive tester, and some time ago also weld inspector. My background, I have about 10 years plus experience in R&D with your universities and our partners worldwide in, let's say, more scientific part of welding. I'm super passionate about TIG welding, so please take everything I said with a little pinch of salt. I'm maybe a little bit biased. About our company, Wolfram Industry, we are manufacturing tungsten since 1911. Means we were producing tungsten electrodes before the invention of TIG welding. We're a family-owned company dedicated to uncompromised quality. We believe quality always wins. We have 2 manufacturing sites in beautiful Bavaria and 1 in beautiful Switzerland. Although the Swiss site is dedicated to R&D predominantly. So the structure of this presentation is kind of meaningful GTAW, so shielding gases, tungsten electrode, a little bit about the arc and the science behind it, because it's really, really interesting, and about welding, because most of the visitors here take a look into how we can be more efficient in TIG welding. So, some picture to start about the shielding gas. I mean, shielding gas, magnificent, and it's one of the most essential components to improve the efficiency of TIG welding. So TIG is somehow misleading because it implies tungsten inert gas welding, but GTAW is more precise because we're not just using inert gases. So mix and doped shielding gases offers a significant potential to improve GTAW processes. Hence, the understanding, varying, and implementing of different shielding gases is a key competence to increase the productivity. So, besides standard argon, consider to use helium, although it's a little bit rare, but you can do fantastic things which argon is just not capable of doing. As an example, increase penetration or create a more preferential penetration profile in all metals. That's kind of the positive thing. Even the most sensitive base materials can be welded with helium. With hydrogen, it can do about the same trick, although it's far more efficient. Against many notations in the literature, the density of the gas is essential for the heat conductivity. Hence, hydrogen is twice, at room temperature, about twice as efficient as helium, but it's limited almost always to stainless steel. But I can say you also can use it in carbon steels. Most welding engineers will say, well, carbon steel, hydrogen, very bad idea. I can tell you with the proper post-weld heat treatment, that's a fantastic idea. You just need to know what you do. And also nitrogen, some heard about. You can, in welding in duplex steels or stainless steel, you can adjust by adding nitrogen the proportion of austenite and ferrite, or reduce components, unwanted components such as delta ferrite. And probably something new, you can also increase the tensile strength in stainless steel without causing an embrittlement, and not by like 2-3%, by like 15%, which is kind of unheard of. By adding a gas, and you increase the tensile strength. A little bit less common components are carbon dioxide, some may heard about, but with carbon dioxide you can change the fluid mechanic or the Marangoni flow, so you can have an extensive penetration, or for like 4 or 5 millimeter in a single pass with the addition of carbon dioxide. It increases the wetting in fillet welds, but also can be used to compensate for different heat loss, like sulfur content, in low amounts, more in the parts per million region. So welder or companies which weld like flanges to tubes can compensate for different loss. There's also the possibility to add oxygen. It improves outgassing and arc stability in aluminum welding, and increases toughness in carbon steel. So it helps with forming acicular ferrite, special composition, where you have an increased toughness without embrittlement by inducing oxygen in a carbon steel weld. So people might think, well, adding oxygen will cause porosity. That's plainly wrong. Oxygen almost always doesn't cause porosity. It's hydrogen or nitrogen which causes porosity. So somewhere in the translation of air and oxygen, someone mixed something up. Porosity is not caused in most metals by oxygen. And nitrous oxide can be used to reduce ozone in aluminum welding by a fantastic mechanism, and it also increases arc stability. So if you're interested in reducing the emission of ozone in your weld shop, go to the gas guys, ask for shielding gases, because this is what the shielding gas can do. But shielding gas is also the single biggest root cause for process instability, and this is due to mostly too short pre or post flow, gas turbulences, and in almost all cases actually, gas turbulences are caused by too much shielding gas. Contaminated shielding gas, especially trace moisture, is one of the biggest issues because it's super hard to detect. And of course, leakage in tubing fittings are causing in the industry, I would guess, annually multi-millions of lost revenue, rework, just unnecessary work or expenses. So porosity, discoloration, tungsten wear, and arc instabilities are linked to problems with the shielding gas. Some pictures of tungsten electrodes. On the left side, there's a tungsten electrode which has too little pre-flow time. If you have a 6-meter torch hose, and on Monday morning you have 0.2 seconds of a pre-flow time, you will burn your tungsten in plain air before it even started the new week. On the right side, you see a discoloration people are certainly familiar with. These colors are caused by non-stoichiometric tungsten oxide, so very high oxides with like tungsten 19, oxygen 38, something like this. They will decompose in an arc because they are not very stable oxides. So if you have discoloration, that's almost always caused to too short of a pre-flow time. So while the tungsten is cooling down, it will be exposed to oxygen. These pictures are taken by a scanning electron beam microscope. Some might have seen that. This is the classic damage mechanism of trace moisture. So H2O, which can diffuse from non-suitable gas hoses into the arc. This causes a plasma etching effect, so the tungsten electrode is actually etched away in a very high temperature, because when H2O is exposed to a very high temperature, this causes a dissociation, or like a splitting of the molecule H2 into atoms, even hydrogen radicals, which just etch away every metal. The next topic, tungsten, the electrode, and all what I'm going to say will apply for all tungsten. Manufacturer, all tungsten, it's really neutral. But the grinding geometry matters. Especially if you weld automated GTAW, if you have variation in the geometry, it will cause process deviation. So it matters. It's like the tire on your car. If you have a Lamborghini and you mount 3 different summer tire and 1 winter tire, and you want to try to climb a hill, you will not be successful. And it's not the car's fault, right? So even the most expensive and most sophisticated welding system will fail with the bad tungsten. A flat tip on the tungsten electrode increases welding time because you don't overheat the very tip of the electrode, and the overall process stability, like penetration, sidewall fusion, is far more stable. And against every myth or half-truth, it will not decrease like arc stability or whatnot. Something about thoriated tungsten. We're still happy to produce thoriated tungsten, but in all cases we have so far where a customer stated the thoriated or the red electrode is far superior than anything else. It's tied to a shielding gas issue. I will take every day, every bet that if someone state only thoriated tungsten work, it's related to the shielding gas issue, and almost always he has excessive discoloration, microporosity, lack of things like that, because whatever happens to the tungsten electrode will happen to the weld puddle. This is so closely intimate related to each other, there's no disconnection of that. It's the bottleneck in automation. You can buy a 100 kilogram wire spool, you can add a bottle assembly where you can weld a full month, but the tungsten electrode is almost always the first part which will fail. So this is the reason why you have to stop the process and you lose revenue. Or often the mechanism are, because a part has a damage, you start to change the tungsten. So you should change the tungsten before you have production reject. And it's an overlooked factor in productivity. I'm welder by myself. You spend at least 20 minutes a day grinding tungsten. Depending where you are in the world, this adds up to significant amount of time. If you have a weld shop with 30 welders, you pay one welder, very skilled person, to grind your tungsten. There are better solutions. And speaking about better solution, our color-coated 175 millimeter rod's the right choice for you. Color is very bad. You need to remove it to get it into the color. 175 millimeter, no welder likes to weld with it. So, get them shorter, laser engraved, and the problem is solved. So, this is kind of a bold statement, but it's just not suitable for a weld shop, in my opinion. So, a little bit about science of welding, or the science, what's happening in the arc. So, the arc is an atmospheric plasma where the gases get excited, so have a higher energy level, or even partially ionized. So they will get electrically conductive. As soon as you have an established weld pool, you have metal vapors present. And those two facts are causing a lot of trouble in the science, because it's super difficult to understand and simulate the mechanisms behind it. Also very interesting, the arc is about twice as hot as the surface of the sun. So if I hold a TIG torch, the temperature gradient from the tip of the tungsten to my hand is far more than the temperature gradient anywhere else in the universe. So even fusion reactors have a higher temperature gradient than a TIG arc. I find that fantastic. It radiates a lot of ultraviolet, visible light, infrared light, which make it perfectly suitable for diagnostic tools such as spectroscopy. Today's method to scientifically investigate arc haven't been here 10 years ago. They were simply not existent. So that's a huge chance for the future of TIG welding. There's also an electromagnetic field based on the Lorentz force principle, which surrounds the arc, pinch it, and accelerating it. And fun fact, the electrons are faster than an Airbus or a Boeing commercial airplane. So a welder is not just something in his hand which is hotter than the sun, it's also faster than an airplane. Noticeable, there is a physical effect, a static pressure from the arc affecting the weld puddle. With very high current, you can indent molten metal just by the arc force. It's called arc pressure. So here a little picture to facilitate the next steps. So left is a picture of the arc while welding, and on the right side is after welding. So the split screen helps us a little bit to understand, because electrons are emitted on the electrode either by field or thermionic emission. So either the inverter or transformer will create enough of a voltage that electrons will leave the electrode. As soon as the tungsten get hot, the atoms in the electrode get so hot that they will send out electrons. So this is called thermionic emission. It travels through the arc column down towards the weld material or the base material through either gas or metal vapor as soon as you have an established weld puddle. It penetrates a boundary layer, so a static layer of plasma over the workpiece, which is about 0.2, 0.4 millimeter thickness, and this is essential how you transfer the energy from the arc to the workpiece. So the electrons are essentially having a kinetic energy. They penetrate the boundary layer, impact the base material, and transfer their kinetic energy as thermal energy to the workpiece. The thermal energy is conducted through the metal. Metal is a very good conductor, to the weld puddle, and starts to melt or even evaporate the base material. So this is a Schlieren image. This is a special optic technique. What we actually see is kind of an X-ray of the arc. So we see the outline of the arc and the very high temperature, but also the tungsten. And this is something I would people encourage. There is a science behind welding. So today we have methods such as Schlieren imaging to quantify if a shielding gas flow is turbulent or laminar. We have high fidelity and high acquisition rate or frame rate imaging techniques where we can analyze in situ how the gas is flowing and how you can increase the gas, the protection of the gas, shielding gas. On the left side, that's something very interesting. It's kind of a snapshot of an arc strike, and those are millions of a second. So what happens in the first 5 millionths of a second? How the partial breakdown ionizes shielding gas, and afterwards how this energy is dissipated with thermal conductivity through the shielding gas. This is a detection or a spectrogram, so we can watch the arc, and by watching at the arc, as we can watch to the sun and determine what it is made out of, we can determine what's the composition of the plasma. So welding is science, it's not black magic. gas tungsten arc welding is highly predictable. It's very repeatable, hence it's ideal for high quality application. Process deviation do have a root cause. It's not a coincidence. Whatever happens, happens for a reason. We might just not understand why this is happening. So a stable arc or a stable TIG process is a result of knowing all factors which influence or might influence the process, and we can optimize them. So that's very crucial. But we also want to take a look, or my personal view, on how to improve welding. We have the chance to work from very small welding companies to major player in the industry, in all industries. And what I've seen, workplace ergonomics. Workplace ergonomics such weld fixtures, tables, positioners. Walk over the trade show and you will see many very innovative ideas how you can take workload off a manual welder. In many applications, low volumes, a manual welder is the way of choice or the way to go to be efficient. So make his job as efficient as possible. Light automation, especially arc voltage control in rotational or circumferential welds or in linear welds, are essential. There's a tight relation between arc length and arc voltage. And systems like this are very affordable and have a significant impact on your productivity and repeatability of your welds. A little bit more modern approaches is to reduce the workload on a welder. If I need to weld, all my attention is focused on the welding, so I can't look left and right. With collaborative or remote operated system, it takes off the manual work and brings the welder into the role of being the operator or the control, the person or the system in control. This has a huge leverage. Don't underestimate that. And we see a lot of approaches to digitalize welding. One of the fierce enemy of digitalization in TIG welding is the high frequency arc start. Having had many chats with manufacturers this week, they always say high frequency arc start can cause problems because of electromagnetic interferences. So a touch or lift start arc is perfectly reliable and doesn't cause any introduction of tungsten contamination in the weld seam. Otherwise, the nuclear industry will not use touch lift start as their preferred method to initiate an arc. So, in summary, I see a very bright future for gas tungsten arc welding, especially because GTAW is one of the few processes where the addition of filler wire and the addition of heat input can be entirely disconnected. So I can have a high penetration with very little filler wire, or I can clad material with very little heat input. In other procedures, it will not work. There are high potential in so-called high current or high energy density welding, where you create keyholes. So north of 400 or 500 amps, where a penetration of a 10 millimeter stainless steel vessel wall is possible. There are some hurdles where the machine manufacturer will overcome, but it has a huge potential. Hot wire system. So the addition of a current on the filler wire provides, in regards of deposition rate, fantastic potential. And once welders start to understand this mechanism, they will use it and increase the productivity significantly. Plasma welding, although not directly related to TIG, plasma welding has in keyhole and conduction mode a fantastic potential to bridge gaps to micro welding and is super reliable. It takes far more training of the welders to manage plasma welding, but I personally think that's a very underappreciated and underused system. I've seen interesting approaches in dual gas systems, so not one single gas nozzle, so dual gas nozzles with the transfer arc, so actually a TIG, it's not a plasma process, it's a TIG process, but with a double shielded gas. So the plasma and the shielding gas doesn't have the same composition. And looking a bit back on the shielding gases, we see there's some interesting combination possible with dual gas systems. Modulated arc modes, such as variable polarity, special curves in AC welding, or DC pulsed welding, or modulated DC pulse welding, helps to increase lack of fusion, increase weld stability, and even can affect the grain morphology in the weld bead. Finer grains can be achieved by modulated arc modes. In general, lightweight structure and alloys, whatever you want to move, if it's lighter, it has the advantage of less energy consumption. Whatever you want to move, if it's light, these thin wall thicknesses, special materials such as aluminum, titanium, high strength steel, and here TIG welding is ideal to make delicate, small, lightweight structures. We spoke about welding, but by definition, if the filler material is not the same kind of type of the base material, it's called brazing. So gas tungsten arc brazing. Some know it as TIG brazing or silicon bronze filler wire. Fantastic possibility, so you don't melt the base material, so you can put materials together, which usually don't belong together. Coming from Switzerland, like cheese industry, so you can have a copper bucket, but on the outside a stainless steel vessel. So at one point you need to fuse them together, and GTA brazing is the ideal process of that. And of course, since it's so stable, process monitor and digitalization is the ideal starting point in TIG welding. So, ask yourself the question, if you set up a process, do I have the ideal gas? Do I have the right tungsten electrode for it? Are my process settings, so the arc properties, are these the right? And do I have the right welding equipment? Can I improve due to automation or to increase ergonomic the performance of the welder? And as always in the industry, be curious, innovative, and open for new approaches. Just because it didn't work 20 years ago doesn't mean it worked today. It wouldn't work today. So there's a lot of pre-opinions in the welding industry. If we be innovative and open for new approaches, we really can increase the value of welding in general and especially in TIG welding. So I would like you to imagine a factory where 99% of the weld seams are passing inspection. They have very little rework or none at all. The welding process causes very low emission in health, safety, environmental aspects. Processes are highly mechanized or automated. Manufacturing is digitalized. And this factory is very likely high in gas tungsten arc welding. So, the summary, when quality matters, the first choice is gas tungsten arc welding. Otherwise, the nuclear industry would not use GTAW. The unused potential of this process can very quickly outperform faster in regards of deposition rate processes in a full cost account. If I just take a focus on the welding, how fast I can weld, that's not the appropriate measure to quantify the efficiency of a weld process. If I have a lot of rework, or if I have to prepare the stuff or the material specially, maybe it's not the right one. So, in my opinion, no doubt, gas tungsten arc welding has a bright future, and having walked for 4 days or now 5 days the trade show, many people are sharing this view. So, you're very invited. Stop at our booth, Hall 5, A18, or contact me or us via the usual channels. And since we have 21 seconds left, probably not too many questions.
Thank you very much, Matthias, for kicking things off today and for giving us some insights on the hidden potential of TIG welding. Well done. And well, we actually have some minutes left for a Q&A in case that you have questions. We have some guests who just arrived. Maybe the question would be, what was it all about? But feel free to ask questions. Right now we have a hand microphone and our colleague will be right there. Just raise your hand.
Ihr dürft auch Fragen auf Deutsch stellen, wir können sie dann auf Englisch übersetzen und zurück. Genau.
Schweizerdeutsch geht auch, habe ich gehört.
Können wir auch, wer es versteht.
Ja.
Mr. Hoiguri.
Okay, so, ja, bin ich gespannt, ob es jetzt Schweizerdeutsch wird oder...
Probably English.
Thank you for that nice presentation. If you were to pick one, the low-hanging fruit, if you were to start, where would you go?
General for optimization.
For optimization.
So, let me go for every step, right? So we talked about gases, tungsten, okay. So first with gases, increase the heat conduction. Go with helium or hydrogen, whatever is possible. Go with the pre-ground electrode with the flat tip. In matter of processes, I would say reduce the heat input to increase process stability, reduce weld speed, will outperform. And in matter of like invest into process optimization, vision systems or light automation will be the right choice.
All right, thank you. So you've mentioned less emissions, for example. Let's talk about sustainability as well. And I remember the first day here at Schweissen and Schneiden, we had an exciting panel regarding raw materials and stuff. And of course, we talked about wolfram or tungsten. So let's talk about sustainability in that regard. We already had this short chat about that, the circular economy, recycling. How do you manage that?
Yeah. So one thing is, the best is use as little resources as possible. Means create not much scrap material, reduce, just making argon gas or the metals we use is high energy intense. So use these resources wisely, sustainable is always the best choice. Instead of recycling, reduce the amount you need. So in regards of a tungsten electrode, do one thing, don't throw it away. Tungsten can be perfectly recycled. It's like copper. The chance to recycling is very, very high. But today, most of the tungsten will be thrown somewhere in a scrap metal, and since it doesn't melt, someone, maybe 2 generations later, will drill a hole in a plate and will get your tungsten electrode and ruin his drill bit. So separation will facilitate the recycling. In a mobile phone, as soon as we know where the materials are, we get a fair chance to recycle them in a proper manner. If we throw everything together, the material is considered lost.
And also, recycling also means less dependencies globally speaking, on maybe other countries and so on. So do you have your company, do you have any dependencies that you're afraid of?
Compared to special alloys or high refractory alloys in tungsten, very, very little. So,
all right,
let's say that. Yeah.
Okay, so thank you. That's it from my side. If there aren't any additional questions, I think that's it for now. So it's a wrap for our first presentation of the day. Matthias, thank you very much once again. And once again, a big round of applause for our first speaker of the day. Thank you, Matthias. So what's coming next in around about 10 minutes?